Hello everyone, previously we had discussed on the topic validate binary search tree algorithm, right? So today we'll be discussing on the topic balanced binary search tree conversion algorithms, right? So now, this has to be balanced binary search tree conversion algorithms basically, right? So it can be anything, right? AVL, tree, so those kind of things, right? So this is fine. All right, let's get into the definition part first. So let's see what the definition part say here. A balanced binary search tree uh, is a BST or the binary search tree where the difference between the heights of the left and right subtree of any node is at most 1. Again, where the difference between the heights of the left and right subtrees of any node is at most 1. So balanced binary search tree conversion algorithms take an unbalanced binary search tree or a sorted array and transform it into the height balanced binary search tree to optimize the search insertion, right? Optimize search insertion as well as the delete operations, right? So again, let me tell you this one again. A balanced binary search tree is a BST where the difference between heights of the left and the right subtree of any node is at most 1. At most 1. This one you have to remember. Simple. Next point is balanced binary search tree conversion algorithms take an unbalanced binary search tree or sorted array and transform it into the height balanced search tree to optimize search insertion and the deletion operations, right? So now let's get into the explanation part, right? So in many applications a BST may become skewed like linked list, right, over time due to the sequential insertions, right? So this causes search operations to degrade from big of log n to big of n, right? So this is one of the what do we call one of the things basically. In many applications a BST may become skewed over time due to sequential insertions, right? So sequentially we will be inserting, right, due to the sequential insertions. So this causes search operations to degrade from usually it's big of logarithmic n, right? So BST, binary search tree, time complexity. So this causes search operations to degrade from big of logarithmic n to big of n, right? Just remember this. To convert the binary search tree into the balanced binary search tree, so we will be going with a in-order traversal approach for the unbalanced BST, right? So we will perform an in-order traversal to get the elements in the sorted order. In-order traversal follows the order left, root and then right. Just remember this one, right? So we will be using the sorted list just to build a balanced binary search tree using the middle element as root recursively. From the sorted array, so we will recursively pick the middle element as root. Left subarray becomes left subtree, right subarray becomes right subtree, right? So both the approaches ensure that the height difference between the left and the right subtrees of every node is minimal, right? So again, so from here, after performing the in-order traversal basically, we will use the sorted list to build a binary search tree using the middle element as root recursively, sorting. So from the sorted array, what we'll do first in order, then sorting the list, right, by making use of the recursion basically, and then from the sorted array we will recursively pick the middle element as the root. Left subarray becomes left subtree, right subarray becomes right subtree, right? So both approaches ensure that the height difference between the left and right subtree of every node is minimal. Let's try to implement or this one, what we call articulate the same thing in the form of algo or the code basically by making use of the Python programming language. So now let's do one thing. Let's define a class for the binary search tree nodes, right? So I'll just go with a class here. So this one is nodes. This is fine. So the first part here would be let's go with the initialization part or the constructor part. So I'll just go with init here. So this one along with the self, I'll go with the parameter val as well. We need it here, right? So this is fine. Now let's go with the node value left child and the right child. So I'll just go with the self dot val, that is equivalent to val. This is fine. The next part would be self dot left. So this is equivalent to left. This is also fine. The next one would be this one. Let me give none, man. So this is fine. And finally the self dot right. So this one has to be none basically. Yep. Now let's do one thing. Let's move on with the next step. So let's go on. Let's move on with the in order. right? So in order function, in order meaning we have to perform the in order traversal, right? So as I've said, as we had discussed in the what do we call explanation, so this in order, let's go with the in order function just to perform the in order traversal, just for the this one unbalanced binary search tree conversion. So this is what we discussed here, in order traversal approach for the unbalanced binary search tree, right? So I'll just go with here def, so I'll just go with the name in order here, root comma array. So this is fine. The next step would be if root, then what we'll do, if root, then we'll be going with the recursion basically, right? So I'll just go with the in order. This is fine. So this one will be root dot left comma array. This is fine. Fine. So why this is showing error here? In order is not defined. Hey, we are using this one recursively, right? What's the problem here? Root comma array I have considered as parameter. If root, this is fine. So then we are going recursively basically. What's the problem here? In order of root dot left comma array. I don't understand, man. This is fine for now. Next, we are just recurring on the left subtree here in the line number 37. Line number 38, let's do one thing. Let's add the current node's value to the array. So this one will be array dot append of this one value of the root. This is fine. The final thing here would be we have to recur on the right subtree as well, right? So this one will be in order. So this is fine. In order of we are recurring on the right subtree, right? So this one will be root dot right along with the array. So why this one I have given in order here, in order root comma array. This is just the function to perform the in order traversal, right? So what's the problem here? Why this is showing right? It's not defined balance. So this is fine. Next step, what we will be doing actually, let's go with one more function, nothing but what we have to do here according with the explanation after the in order traversal, this one, after performing the in order traversal to get the elements in the sorted order. So we haven't this one, we haven't sorted the array to the binary search tree, right? Let's sort this one first, right? So let's do that one. So I'll just go with def sorted array to binary search tree. Let me pass the array here. This is fine. If not array, so this is fine. Then return none. Right, so this is fine, man. Base case, this is for the empty array. Next, let's go with the mid. We have to calculate the mid, right? So this one will be len array by 2. This is fine. Next part would be we have to go with the middle element that becomes root basically, right? So this one will be root equals node of this one array of mid basically, right? So this is fine, man. Yup. Now next part, let me do one thing. So we are just going with the middle element that becomes the root. Now let's consider the sub array, left sub array, nothing but the left subtree of the left subtree, and the right sub array of the right subtree. So this one I'll just give here root dot left equals we have went with the sorted. Why this one is not taking the recursive part basically everywhere? Did I do anything wrong here? Or this one has to be, or this one initialization part. So this one I think, I believe, I don't know. So this one has to be indentation problem, I believe. I think so. So that is the reason we cannot, we are not able to go with the recursion actually. Let's do one thing. Let's check the same here. So this one has to be same as if. So now if I make use of, yeah, now this is showing sorted array to BST. So this one node here also, it is showing nodes actually, not the node, right? So we have to go with a basically node itself. This is fine. Now this also became correct actually. Nodes by 1 second, just give me a second. So now let me give here array of basically mid, right? So let me give colon mid here. This is fine. Next let's do the same thing for the right subarray. We have to go with the right subtree, right? So this one has to be the root dot right here. So this one sorted array to the BST. So this one has to be array of this one for the right. So we have to move mid plus 1, right? So this is fine, mid plus 1. So let me give colon here. This is fine, man. So the next step would be we have to return the root. So I'll just go with return root. This is fine. Yep. Now the next step would be the step 4 or the final one would be, so we have to go with the function to print the binary search tree in order. Just for the verification purpose we are doing this one, right? So this one I'll just go with def print. I'll just go with in order. This is also fine. Of root. This is also fine. If of root. Yep. So now let me go with the print in order. So this is fine of root dot left. Yep. Again let me go with a print statement here. So this one will be root dot val comma end equals, let me leave the space here. This is fine. Also let me go with print this has to be in order root dot right. So this is fine. Now we are done with the print in order this one, what do we call method or the helper function, right? So this is fine. Now let's go with the original unbalanced binary search tree, right? So let's consider like this. So let me show you the sample or the build basically. So this is going to be, let's consider this example. Let me consider 10 here. So left, for the left let me consider 5, this one, this is fine. And for the right it has to be left dot left. Let's consider, we have to go with the left dot left as well, right? So this one let me consider 2 here, and again this one let me consider one more left here. This is skewed towards the left, right? So right we have 15 basically, right? So right we have 15. So this is unbalanced. This is the binary search tree. See here, left value we have 5, and for the 5 we have 2, and for the 2 we have 1. So basically the values at the left, it is smaller than its parent basically, right? Or the root value basically, right? So this is fine. Right value we have only one value, that is 15, which is greater than the root value. This is fine. This works, but this is unbalanced basically. Level C here we don't have another this one, right? This one again we don't have any this thing as well for this level as well as for this level as well. And also here instead of left and the right subtree we have only the left one, right? So this is left skewed basically. This is skewed left basically. This is fine. Now let me delete this one entirely. So let's do one thing. Let's go with the original unbalanced binary search tree. And so this is root equals node of 10. This is fine. The next one would be root dot left. So equals, we consider node dot this one, node of 5 basically. This is fine. Next part is root dot left equals node of. So did I call this one nodes, man? So why this is showing? Oh, this one class nodes I have considered, right? So this one has to be class node. So that is the reason it is not taking anywhere node. So now the error is gone. So this is the reason. This is fine. So I didn't check this one at all. So this one here, let me give node 2. This is fine. Now let me we considered the complete left skewed tree, right? So I'll just go with left dot left. So this one let me go with node of 1. So this one has to be capital N. Let me go with the capital N. This is fine. The final one here would be root dot right. So let me assign this one to the node of 15. This is fine, man. Now this is the original unbalanced binary search tree. The first step here would be we have to convert the binary search tree to the sorted array. So this one will be array of this. So So let me call the in order here, in order of this one, root comma array. The final one is we have to print, let's print something for the this one, what do we call, interactive purpose, this one sorted array from BST. Initially let's print the sorted array from the binary search tree, the second step or the third step that we did, right? So this one, let me pass array. This is fine. The next step would be, so we have to convert the sorted array to the balanced binary search tree, right? So this one is balanced root equals, let me call the sorted array to BST function here. Let's pass the array that we have considered. So this is fine. So the finally what we are doing here, the last step, we have to print the in order of the balanced binary search tree, nothing but the result. So let me give print here, print of in order of this one, let me go with balanced binary search tree, right? So this is fine, in order of this is fine. So now it will be end equals this is fine, man. Next part here would be print in order. So this one will be print in order of balanced root. This is fine. So we are done with the coding part, right? So we are done with the coding part, right? So now if I run this one, I have explained this one step by step, right? So whatever we have discussed, we had discussed in the explanation part, right? So the same thing we have articulated in the form of code, right? So algorithm, whatever algorithm that we have written using the Python programming language, so this is same, right? So that we had discussed in the explanation. Now let's do one thing, let me run the code here. Let me run the code. So I'll just come here, just give me a second here, 1 second. Yep. 1 second. Yeah, let me give control J here. So this one, let me give Python v file name dot py. So see here, the sorted array from the BST, we have 1 2 5 10 15, right? So this is sorted in the ascending order, right? 1 2 5 10 15, and in order of the binary search tree, balanced binary search tree, so this one has to be 1 2 5 10 15, right? So in order, again it follows the order, this one, left, root, and then right. I'll just give here right. Let me write this one entirely, don't get confused here, right? This is fine, man. Again, this one sorted array to binary search tree, basically whatever we have written here, just give me a second here, 1 second, let me remove this one. Yep, this one follows left, right, and right. So this is fine. So here sorted array from the BST, so this one we are considering, right? So see here, balanced row. So we are printing sorted array from the binary search tree, and we are printing the array basically. So this one basically used the middle element 5 as root. So this one used middle element 5 as root. See here, middle element that we got here is 5 basically. This used 5 as root, this one, right? So this is fine. Now it recursively built left and right subtrees. So now left subtree 5 is mid and 1 2 is left, 5 is mid now. So this one I'll just write mid, and the 10 and 15 are right basically, right? 10 and 15 are right. So this is fine. Now in order traversal of the balanced binary search tree still produces a sorted array, right? Confirming the binary search tree property is preserved, right? So see here, we have got the in order 1 2 5 10 15 again, right? Again, in order traversal of the balanced binary search tree still produces the sorted array itself, confirming BST property is binary search tree property is preserved, right? So we are getting the desired output, which is absolutely correct, right? So this is it for the this one, balanced binary search tree conversions algorithm, right? So now I hope this part is completely clear, man. I mean this algorithm is completely clear. Now let me summarize whatever we have learned so far. Just try to remember these 3 or 4 points, man. Balanced binary search tree conversions, what it does, it optimizes the binary search trees for the search operations, right? So this is fine. Again, balanced binary search tree conversions optimize BSTs, binary search trees, for the search operations. The second one is the algorithm uses in order traversals to to extract the sorted data and divide and conquer to reconstruct the height balanced binary search tree. This is fine. The third one is time complexity would be big of n, right, for the traversal, and big of n for the reconstruction. Overall it would lead to big of n itself, right? Overall it would lead to big of n. So this would be the time complexity basically, right? So the space complexity would be big of n as well for storing the sorted elements, right? So the time complexity and the space complexity would lead to big of n both, right? So these are some of the important points I found that I wanted to discuss with you guys, right? So this is it for the balanced binary search tree conversions algorithm, right? So tomorrow what we'll be doing, we will be discussing on the topic, or we will be going with the this one, we'll be discussing about the segment tree algorithm, right? So we'll be discussing on the segment tree algorithm tomorrow. For now, this is it. Thanks for watching, guys.